Let me start my talk. First of all, thank you for inviting me this opportunity, and I will let me introduce our project, so-called Onokoro and ESPRI, and I'm Juzo Zenihiro from Kyoto University, and so let me start from this slide. Basically, we want to understand the nuclear matter itself, and basically, nuclear matter properties characterizes not only the finite nuclear, but also the astrophysical phenomena. And at the same time, nuclear matter has multifaceted aspects like clustering or correlations, or in the case of the high density case, some strangeness appears. And this means maybe the appearance of this kind of correlation or a kind of impurity in the nuclear matter is the key to understand such matters. And of course, and maybe as you know, recently more fantastic result from the theoretical calculations, and Stefan Tippel predicts this kind of clustering occurs in the dilute nuclear matter. Dilute means the density is something lower than the 0.1 saturation densities. And in this dilute nuclear matter, many kinds of clusters, not only in the alpha, but also deuteron and triton and helium-3 evolves, and which is very deep. The fraction depends on the density or isospin asymmetries. And so from this side, we want to understand this kind of dynamic nuclear matter, and so maybe this kind of clustering itself, it's the key to understand such nuclear matter properties. And so our strategy is something like this. To understand this nuclear matter, one side, we want to precisely know the nuclear matter EOS as a point of view of a uniform nuclear matter. At the same time, we want to see really this kind of clustering is appearing in the nuclear matter. So in the nuclear matter system. So for this purpose, we approaches this study from the two different ways. And so next, we need to, so from the experimentalists, we need to do this kind of study with some finite system. So in the case of a finite system, Stefan Tippel also predicts a very nice result from his mean field calculations. And he says that on the dilute surface on the heavy nuclei, alpha clusters developing like this way. And it depends on the isotopic changes. And this is the case of the thin isotopes. And this dashed lines are the density itself. And the solid lines are the alpha particle density. And it also shows this kind of alpha number particles is decreasing depending on the neutron numbers. So we want to see that this kind of clustering itself, and for this purpose, we use these two methods, experimental reactions. One is the alpha knockout reactions to deduce this kind of alpha cluster density, and the other is the proton elastic scattering to deduce the matter density, matter or proton or neutron densities. Okay, so let me introduce our previous studies before going to the current project. Okay, and one is the pilot experiment of thin isotopes at RCNP, and another is elastic scattering at RCNP. Okay, first,
we have a question.
yes.
Because my question is about appearance of alpha clusters
Yes.
in the surface region of nuclear matter. So
This one.
Yes. So it is not obvious to me whether this should happen, because the surface region of atomic nuclei is not low energy, low density phase of nuclear matter. Okay. So atomic nuclei are finite systems. In the surface region, local density approximation should not work. Things are defined by the gradient terms, etc. So somehow to say we have lower density in the surface, therefore alpha clusters, should be there, I think that is very difficult to justify. Well, could you dwell on this?
Yeah. So yes, I think so. Yeah. So yes, it's very difficult to finalize the alpha is really there in even if we measure the knockout alpha from the reaction measurement, but it's a kind of proof of the existence of this kind of correlation around the surface region. Is it okay? Oh.
Yeah, I think this is a very good topic for discussion later on, right? So let's continue then.
Can I continue?
Yes, yes, please.
Okay, thank you. Thank you. Okay, so yes, as I said, we already performed this kind of experiment at the RCNP with proton proton beam, polarized proton beam at the medium energy regions, and the targets are these thin isotopes, and we also use the very good magnetic spectrometers, two magnetic spectrometers, to analyze the momentum of the proton and the knockout alpha particles. And in this case, we measure the knockout proton and the knockout alphas scattered each. These are each angle scattered and the knockout angles. And finally, we detected, and these are the spectrum, the missing mass spectrum of the knockout PP alpha reactions of each thin isotopes. And so finally, the alpha particles are really there in the thin isotopes. And we also observed this kind of strong transition at the low line, including the ground state, even higher line state. And we also finally observed the decreasing tendency with the increasing mass number, like this way. And this tendency is almost completely the same as the prediction, but the absolute value is now it's normalized. Okay. So it's a kind of, we can say that it's kind of the signature of the surface alpha formation, and the result is already published in this science paper. And these guys are the main collaborators who analyze the data. And okay, then we go to the next topic about proton elastic scattering to determine the density information. And here's the result from the previous experiment at the thin isotopes and the lead-208 and the calcium-48. And this experiment is are also done at the RCNP, Osaka University, with the same facility and same device. So, okay. Anyway, so we have already, in the case of the proton elastic scattering, already established how to determine the density distribution of the stable nuclei, like lead, tin, and calcium isotopes. Okay. We also performed about the zirconium case like this way. Okay, from the density information, we can know the kind of neutron skin structure, which is very related to the nuclear matter equation of state, especially for the symmetry energy. And for this study, usually double magic nuclei are used, like lead-208 or calcium-48 or tin-132. But this one is the unstable nuclei. So, but here I showed some experimentally constrained region of the symmetry energy. Still, it has large ambiguity and saturation density regions. And maybe we think this situation is not, it's difficult to improve this situation because from the experimental point of view, it's very difficult to determine the skin thickness. It's a very tiny difference between the neutron and the proton density radii. But we have the density information, density profile itself. So we can clearly see that this kind of structure in this density information. So we recently we've developed a new way to how to say judge the symmetry energy parameters. One is the isoscalar and the isovector density map, and this one is already introduced by Sagawa-san in the morning his talk, and it's a kind of a new way to see how to relate to the EOS itself with the density. And we can judge which interaction, which mean field is fitted to our experimental result or not. And the other way is this kind of the density difference between the two isotopes. In this case, this is a calcium case, and the difference between 40 and 48. And this red shaded area shows the 8 excess neutrons between the calcium 40 and the 48. And this magenta is proton difference, density difference. And we have already checked these correlations very related to the symmetry energy parameters. Okay, so this is a little bit detailed about the density difference information. For example, in the case of calcium, we took the ratio between this amplitude ratio, which is R value, and if we plot this R value into this two-dimensional plot, one is the R value in the calcium 40 between the two isotopes, and the other x-axis is neutron skin thickness in the calcium 48. And these two hatched areas are the experimentally determined region from the same result. So this ratio can be constrained more strictly than the case of the skin thickness. So this is our way, our new method to judge the mass theoretical models. Okay. Okay, so let's go to the next. So here is the main topic of my talk, the Onokoro and ESPRI project. And one is we recently launched a new program, experimental program to measure the cluster knockout reaction, not only alpha particles, but also all the triton or helium-3 or deuterons. And so and we want to know how many clusters exist in the heavy finite nuclei. And in the case of alpha clusters, maybe we can say something about it's very in the case of the very heavy nucleus, like alpha decay nuclei, maybe the preformed alpha information can be obtained from these reactions. And also, it's a little bit difficult to how to say understand the reaction mechanism itself in the case of deuterons, because it's easily break up. And but thanks to the recent theoretical reaction model progress, and we can how to say quantify the breakup process, and maybe we hope we can extract such a deuteron clustering in the nucleus. Okay, and maybe the triton or helium-3 cases, there's no data ever. So this is the first observation of this kind of triton helium-3 cluster cases. And already this project is funded in Japan. Okay, and maybe you know the cluster knockout reaction itself is based on the successful PPN reaction at the RIBF and the RCNP, and this probe is already established to deduce to extract the particle information in the nuclei, and now these reaction theories are now developing by the many collaborators, and like this way. One is the DWA plus AMD calculations, and this is for the alpha knockout reactions, and the CDCC with DWA is for the deuterium knockout case. And we also plan to measure the more precise information from the elementary process of each knockout reaction. Okay. And we plan to measure these experiments at mainly three sites in Japan. One is as I said, RCNP, and the methodology is already, experimental techniques are already established. And the others, the RIBF at Riken and the HIMAC at QST. These two are the heavy ion facilities, and we plan to measure the unstable or very heavy ion, heavy nuclear case at these two facilities in inverse kinematics. So in the case of the inverse kinematics, we need to develop the new device to measure the recoil protons. Okay, so this is the main development of this Onokoro project. Okay, this is a new device, so-called Togaxi. It's kind of the telescope with consists of the silicon strip detectors and ZAZZ inorganic scintillators. And so the development is already now ongoing by the many PhD students. And so this in this month, we also plan to test this prototype detectors at HIMAC. Okay. And our plan to measure the in near future, we plan to start with the calcium isotopes. These experiments are already approved in RIBF and the RSNP. And so first, we want to measure this long calcium isotopic chains. And maybe it followed with experiment of thin or lead or more heavier region nuclei. Okay, so next is the proton elastic scattering case. After the establishment that for the stable nuclei, we extend our method to the unstable region. So so we call this project the ESPRI project to measure the proton elastic scattering in inverse kinematics. And as I said, this is a kind of complementary experimental program to the knockout reaction measurements. Okay, so okay, this is the next. So our plan to measure the proton elastic scattering for the calcium 52. And this is the next flagship for our project. Okay. And I will okay. So here I listed our ESPRI project ESPRI measurements so far at the heavy ion facilities like this way. So now for the stable already done at the RSNP, like lead 208 or calcium. And in the case of the nickel unstable, in this case is nickel 70 was done at the GSI. And so in the case of carbon 16s, also done at the RIBF. And recently, the T132 was measured at the RIBF. And we have successfully see the kind of correlation. So here's elastic events. This is a recoil proton energy and angle correlations. And here's very preliminary result. It a kind of a cross-section, diffraction pattern of cross-section in T132 was observed. Okay. And to measure the ESPRI proton elastic scattering for calcium 52, we need some upgrade because the beam intensity is relatively small compared to the case of the T132. So we need to increase the more accept solid angle of the detectors. And so this is we call the ESPRI Plus system combined with the new solid hydrogen target. I mean, this is a multi-layered solid hydrogen target. Existing one is just a one layer, and but we want to increase this 2 or 3 layers. And now, now we start the development, and we also want to use the Togakushi telescope recombined with to optimize this measurement. Okay, so finally we can measure the scattering experiment with very rare RI beams. The intensity is less than 10 kilo CPS or something. Okay. This is a little bit details, but so here we show I show the the case of calcium 52, what we can see from the density information. And here's the this is just a mean field relativistic mean field calculation of the calcium 48 and the calcium 52, and it's difficult to the difference between these two by this plot, but if we plot this like this isoscalar and isobector map, we can see the difference between the two, calcium 48 and the calcium 52. And okay, and the right side is kind of the isospin symmetry distribution in the each nucleus. So in the case of calcium 52, the isospin symmetry is very large, of course, very large. So we can assess on the such neutron-rich matter properties directly if we measure the calcium 52 the density. Okay, sorry. So here, these regions, our method of proton scattering is very sensitive to. Okay, if we see the density difference between the isotopes, so here the green is the case of the calcium 40 and 48. So this is 8 excess neutrons. But in the case of 48 to 52, we can see the 4 excess neutrons in very outer regions. And if so, here this region is kind of corresponds to this region in the case of the isospin asymmetry distribution. So here is a very neutron-rich system. The isospin asymmetry is more than 0.5 or something. So we want to see this region by the density measurement. Okay. Okay, so this is our history, ESPRI history. We already measured some unstable nuclei like this. And recently we have measured the T132. And the next target is calcium 52. And maybe next is more proton-rich side of the tin isotopes. Okay, sorry. Time is, how much time left?
Few minutes?
2 minutes? Okay.
Few.
A few minutes, okay. So this is a kind of advertisement, but we have very recently started some new project, so-called we call ESPRI Star, and this is we use the same proton elastic scattering, but from the isomeric state nucleus. So that means that we can measure the directly the excited state density information by using the isomer beams. And so we want to, so as RI beams open the new degree of freedom, isospin degree of freedom. So maybe we hope that this isomer beam will open the new another degree of freedom, kind of excited energy or some other quantity, like spin or finite temperature. But the temperature is maybe a little bit different. So we need some more discussion with maybe theorists, and we want to yeah. Anyway, we want to measure this new experimental project with RI isomeric beam and at high Mach. So by tagging the isomeric state. And so this is a kind of a test of the we plan to measure first at the beginning with the nitrogen 16 0- state. And so if we assume this kind of density, ground state and isomeric state, maybe we can measure the difference between two. So, so I think we think this is feasible to deduce the kind of this surface density structure of the isomer nuclear, isomeric state of the nuclear. Okay. Okay, let me summarize my talk. So we have started a new project, so-called Onokoro and ESPRI. And one is a cluster knockout reaction measurement, and another is a proton elastic scattering. And each of them extract the cluster density information and the proton neutron density information. And from this result, we want to understand finally, we want to understand the clustering formation in the nuclear or nuclear matter. Okay. So from this study, this is a rather final future goal, but we want to establish the new picture of the more dynamical picture of the nuclei. It has a kind of tendency to prefer the non-uniformity or anisotropy system with this clustering formation program. Okay, so this is a really final summary. So maybe I don't have any time, so let me stop here. Thank you so much.